Welcome back to Applied Mathematics. In this video, we're going to be looking at some techniques for calculating the area of an irregular figure. The first one is fairly straightforward and probably something you're familiar with. So let me get my head out of the way and let's dive right in. Let's say that you are trying to calculate the area of this rectangular region, which measures, 37.5 centimeters by 16.8 centimeters. But there are three cutouts, each one in the form of a circle whose diameter is 4.5 centimeters. Well, to calculate the area of this region, you're simply going to take the area of the rectangle and subtract the areas of the three circles. And yes, I literally write out my instructions in pictograph like this. When I'm doing this sort of thing, it helps me remember what I'm trying to do. Right? I've got a rectangle. That rectangle has length 37.5 centimeters, and it has width 16.8 centimeters. I've got circles. The area of a circle is pi times the radius. Right? We're given the diameter is 4.5 centimeters. The radius would be half of that, 2.25, or I'll round it to two significant figures and call it 2.3 centimeters squared. And we have three of those circles, so that's why I multiply by the 3 out front. 37.5 times 16.8, my calculator tells me, is 630. That should have three significant digits, which means that that 0 is significant. I'll put a decimal point on it to remind myself of that. That will be in square centimeters. And then I've got 3 times pi times 2.3 squared. And if my calculator will actually listen to me when I punch in these buttons, I get 49.85, etc., but I only have two significant digits, so I will round that and call it 50. Again, that 0 will be significant, and that will also be in square centimeters. Finally, I can add these things together, and I get that, I can subtract these things, and I get that 580, again, to the nearest whole, square centimeters, is the area of the figure, not including those holes. I strongly suspect that you have seen this sort of a thing in the past. It absolutely works whenever you have shapes that are even relatively close to the shape that you're looking at. Right? If those were not actually perfect circles, but were slightly elongated ellipses, well, they're still close to circles. You can still use the same formula and kind of hope for the best. It will give you an approximation instead of an exact value. But if you look at the diameter as you rotate the ellipse about, and you kind of figure out what the tolerance of that measurement is, then everything still works fine. The other one is when things get a little bit crazier. What if you don't have a shape that is in any way, shape, or form something you have dealt with in the past? What if you have something that looks like this? How do you calculate its area? All right, well, first of all, why might you calculate this area? I've seen this as a way of thinking about things for an artistic design, right? If this is the shape that you've decided that the slab is going to be for the tabletop that you're about to build, well, figuring out the area of it might help you calculate how much of a sealant you might need, how much varnish you need for it, how much paint it's going to take. Calculating that area and then also knowing how thick it's going to be will tell you how much lumber you need in order to build it, or how much cement or whatever material you're going to be using. Another place that this sort of thing comes up all the time, one of the things that I'm a little bit more familiar with is, well, what if you are trying to calculate the area of something on a map, right? A lake, or even just a property that borders along the road as it curves around on a hillside. You can use this technique for those sorts of things as well, and that's something that we'll explore a little bit more later on, but for right now, we're just going to look at this in the abstract sense. So, the technique we're going to use is to try to come up with a way of approximating this using shapes who we understand how to deal with. I'm going to look at a trapezoid approximation, or sometimes it's called the trapezoid rule. And the way you set out to do a trapezoid approximation is you divide up your shape into equally spaced pieces. And you draw a whole bunch of parallel lines equally spaced. These lines are all different lengths, but that's okay. They are all parallel to each other, and they are all the same distance apart. Those are the important features. We're going to go ahead and measure that distance between two things. Let's say that I know that that distance is 2.8 centimeters. Then we're going to measure the length of every single one of those lines. All right, this first one is 3.2 centimeters. The second one is, I don't know, 8.7. 9.1, 6.8, 5.9, 7.1, 7.7, 8.6, 9.0, and 5.2. All right, just measuring all of those across. And then from there, I am going to turn each of these into a trapezoid. We can calculate a trapezoid by taking the average of the two parallel sides and multiplying by the distance between them, which we know up here is 2.8. And we can do that for every single one of these trapezoids. And by playing connect the dots like this, you end up with something that is a pretty reasonable approximation of the shape. There are going to be some places where your trapezoid extends outside of the shape. There are going to be some places where the shape extends outside of the trapezoid, but it's a fairly reasonable approximation. One of the interesting things that comes up when you're trying to calculate this by hand is that the trapezoid actually works to your advantage. Because you're going to take b1 plus b2 over 2 and multiply by h. And then you're going to take b2 plus b3 over 2 and multiply by h, and so on down the list. Let's put one more in before I put the dot dot dots. Everything has an h. Everything has an over 2. I can factor all that out and write h over 2. I've got B1, the length of the first side. That's going to be this 3.2. And then I've got 2B2, because it shows up here and there. That'll be the length of this side. I've got 2B3, and then everything except for the last one will get multiplied by 2. All right, the first one and the last one do not get multiplied by 2 because they're only in one trapezoid, and everything else gets multiplied by 2 because that same side is in 2 different trapezoids. So you can go through and you can plug all of that in, and you can get a result, and it 100% works every single time. But that's actually still kind of annoying because you have to type everything into your calculator. It gives you a really big expression that's a little bit difficult to work with. So for that reason, I'm going to go with the computer method instead. The trapezoid rule is a well understood method of approximation. And so computer programming tools, I'm going to use SciPy, the scientific Python package, have it built in. That's right, I'm going to write a program in order to do this. And please don't panic. If you have never done anything remotely resembling computer programming before, you're still going to be able to get through this because it is that easy, and I've done almost all of the work. All right. When you write a computer program, the first thing you do is load packages. They're called different things in different languages. I use the Python programming language, which calls it packages, and I'm going to use 2 packages. The first one is the math package. The math package has things like a square root, a sine, a cosine, and so on. The other package I'm going to use is the SciPy package, and specifically the SciPy integrate package, which is where the trapezoid rule lives. Right, I'm going to, because SciPy integrate is a mouthful, I'm going to call it SI. And that's really the hardest part of this process, is understanding that that's what you need. Now I'm going to come down to the next section. And it says, modify this section to represent your measurements. The length, it tells us, is the distance between lines. I had from a previous problem here 2.0. Now I need to replace it with what I got from that figure, which was 2.8. And then I have widths, the measurements of each of those individual parallel lines in what we call an array. An array in Python means something that starts with a square bracket and ends with a square bracket, and then has a bunch of values that are all separated by commas. That's all it means. So I just delete all of the stuff that's already there. I'll start on the left side. My first measurement was 3.2. I will type in a comma, and my next one, 8.7. And I'll just type them all in. And then there is one last command. It says do not modify because it's already set up to do exactly what we need. It is going to print the result of using the trapezoid rule, taking in all of the widths and the length that we just typed up here. Typing all of that in, I can go up to runtime, and sometimes, depending on what you've been doing, this link that says restart session and run all may or may not exist, or it might just say run all. Whenever it's available, go with the restart and run all. That will clear any old data. And it warns you and it says all the old data is going to be lost. I want that. So let's go ahead and run this. You can see that the play buttons kind of changed shape for a little bit. And the number down here has updated. 187.8 0.87999999999997. All right, that's our area. I only have two significant digits, so I will round that. I'm going to call it 190. And then I have to remember, well, I plugged all this stuff in using the units of centimeters, so this area is going to be in centimeters. But the computer has done all the work for me. I don't have to do any calculations with a calculator. I used the computer program, which was a lot easier to read and understand what I was typing in. And I got that the area was 190 square centimeters. Is that actually the area of the figure? Well, no, but to within a reasonable approximation. Generally speaking, I usually say that we lose one significant figure or maybe half a significant figure whenever we do an approximation like this. So our usual rule of thumb for significant figures is that if I write 190 square centimeters, that means anywhere between 180 and 200. I'll broaden that a little bit and I'll say it's probably somewhere between 170 and 210. So we've lost some precision because we did an approximation in the first place, but that's still not that bad and it's relatively straightforward. The last thing that I want to mention is the program that I used to interpret my Python programming. I used a web service called Google Colab, short for Collaborate, which allows you to share and work together on Python code. I will share a link that you can use to get into that system. You should then be able to copy that file and modify it and play around with it, replacing those values with the things that are useful for a particular application that you're looking at. I hope that you find it to be relatively straightforward. If you have any questions, you're always welcome to reach out to me. Otherwise, I'm going to wrap up with that. Thank you as always for joining me, and I'll see you in the next video.